so, but with the additional functionality that you can run these arrays, store and manipulate these arrays in the GPUs. And additionally, it also gives you the functionality of automatic differentiation for building and training neural networks. What I mean by this is essentially it gives you a better way to train your model for the gradient descent and so on and so forth. And lastly, it is quite simple to develop and train models using this library. Now, throughout the whole course of this tutorial, I'll give you some examples about of each of these key factors, and hopefully you get a quite good enough grasp of how to use this library. Right, and in this image, you can see the rising popularity of PyTorch library as compared to something like the R language, which is again a language used to develop and learn statistical machine learning and so on and so forth. Now, in this tutorial, I'll be using the free tier Google Colab notebook. But if you wish to run PyTorch in a local system, you'll have to essentially go to this website and install the corresponding library functions. So yes. Okay, so this is the sorry. Okay, so this is the official PyTorch library website essentially. And then if you wish to install PyTorch library in your local system, you first have to which CUDA version you have to install. So to do this, you have to do NVIDIA. I hope these text is quite visible. Let me maximize. Yeah. So once you do this, you will find that your CUDA, you want this particular version, the CUDA version. So in my local system, it is 12.7. So if I wish to install PyTorch in my local system, I have to find the appropriate version that is compatible with mine. So it is, let's say, with the new PyTorch build is stable 2.6. We'll use that. My machine is Windows system. I want to install it using pip. Language is Python, and my CUDA version was 12. What was it? 12.7. Yeah, 12.7. So we'll select, okay, there is no 12.7 here, but let's go 12.6 if that's compatible and see how it goes. So copy this command here, and in your terminal, you just paste it and you're good to go. Yeah, so as you can see here, although my machine already had PyTorch installed, but once you run this code, your system will have PyTorch installed. Now, if you want to see if Python is successfully installed or not, you can just check like so. Zoom, yeah. So I'll import Torch. And then I'll print the version of Torch installed. Yeah, so my PyTorch version is 2.00. It is quite older version as compared to 2.6 that is recently launched, and it has the support for the GPU, which is called the CU 11.8. What this means, I'll explain later in this tutorial. But yeah, this is how you set up PyTorch in your local system. Now, once you're done that, let's look at the example. Yeah, so first, before we deep dive into PyTorch, let's just look at how you would go about training a model using the basic NumPy arrays, right? So let's say we have a third order polynomial function and we want it to replicate the sin x function, right? So first, let's start by beginning the import of the NumPy library. And then we'll begin by defining the inputs that we want to pass to our models. So it will be, okay, so linspace, let's use linspace. Okay, let's go with math. Okay, so we'll take the inputs from negative values of pi all the way to the positive values of pi. And we want, say, 2000 samples, right? So essentially, linspace is a function defined in the NumPy library. And what it does, it essentially takes the beginning of the value and the end of the value and gives you equidistant values to the number of that you require. So let's see if it does what it should. Okay, so number of values. x, and then we want to see what these value are. So x, and in this case, it should be yeah. So there are 2000 samples, and each of these samples are around 0.03 distance apart. So it goes from the negative values all the way to the positive values here. Right, so we have the inputs defined. Now we want the goal labels. So essentially the value of y, it should be numpy dot sign and x. Let's see if it is the value that we want. Yeah, we have the value, the goal labels y. So these y will be the actual goal labels. This will be the input. And now we want to train the third order polynomial function. Right. So in order to do this, let's first define the coefficients to each of these polynomials. So we'll begin with a. So we'll use the random function from NumPy. Yeah, a, b, c, d. Good. Okay. So these functions will give you the random coefficients of the function that is in slash to some random values. And the learning rate for our whole problem is defined as 1 e minus 6, which is essentially equivalent to 10 to the power minus 6. Now let's go about training this model, right? For time step t in a range of 2000. Right, so we want the y prediction to be equal. So first we'll use a, and then the second coefficient, which will be multiplied with the first order polynomial. The second coefficient, which should be multiplied with the second order polynomial, and it's defined as star star 2. And lastly, the final coefficient, which will be multiplied with the third order polynomial. Yeah. So we have the function defined as what? We have the function defined as so. Now we also need a loss that will define how is our model being trained. Like, is it being converging? Is it deviating? So all of this will use the squared error for our purpose. So this will be the difference between the predicted output and the goal labels here. And then we will take the summation of all the values here. Now, let's say we want to look at how the model is converging at every 100 time step, right? So at every 100 time step, I want to print what my loss function is. So let's go with it, and then the loss. Right, and now comes the interesting part. How will you go about optimizing this model? So we need the gradients. So yeah, gradients for the y prediction. So if you are familiar with machine learning, you will understand that the gradient is defined by the partial differentiation of this loss with respect to the y prediction. So if you partial differentiate this value squared, you will end up with something like this. So all that is left. Now this value will have the coefficient of our gradients. Now all that is left is to calculate the gradient of each of our coefficients. So for grad A, it will just be the coefficient here because there is no polynomial involved. But for grad B, gradient B, essentially, we'll have to multiply this coefficient with the first order polynomial. And we'll do so for all the others. So we have B, C, and D. So for C, it will be multiplied with the second order polynomial. And for D, it will be multiplied with the third order polynomial. Now, this will give us the gradient values, and all that is left is to update each of these weights of A, B, and C, A, B, C, and D essentially. And then we'll get the final coefficients like so. So we subtract the original value with the learning rate multiplied by the gradient that we have calculated just before. And we'll do this for the others as well. CPR, yeah, okay. Now, once we run this, we hopefully will get the optimized value. And to check it, let's print what it gives us. Okay. So yprint, let's go with the results. The final one would be y equals, we have A plus, we have B multiplied by X plus, for this, we have C multiplied by X to the power 2, and then we have D multiplied by X to the power of 3. To the power of 3. What does it say? Invalid encounter in power. Oops. Where did this 8 come from? Yeah, okay. Yep. So each of these values for some reason are not a numbers. Why? Loss squared. Good. Oops, we're just printing at, okay, so for the hundreds times 10, and if is equals to double line, that is where we want to print the values. Yep, there we go. So we have the original values here. This is how initially, as you can see, for the first 100 time step, the loss value is quite high, but as we keep on iterating, the loss value keeps on decreasing. And lastly, we have the results like so. Okay, so the problem here, as you can see, the values of A, B, C, and D are again with 2,000 different instances, but but this is not what we require. We want the final values, right? So one thing we can do here is that for each of these gradients, we'll just pick the summation over the whole input. This will give us the final coefficient of our values of each of our coefficients. A plus B times C to Red Viper should give you this. Let me see what it is randomly printing. Okay. Viper, what is going on here? So the value of y is not getting printed appropriately. So what went wrong? B times C. asterisks. Yep. Okay. Now we should be good. Yep. Okay. So yeah, so finally, as you can see, we have the final coefficients of A, coefficient of B multiplied by X, coefficient of C multiplied by X square, and lastly, the coefficient of D multiplied by X cube. Now, although we see this results here, but it's difficult to visualize what it actually means, right? So to better understand, let's see what optimization finally does. So first we have the original values here. We have the goal labels. Let's call it goal labels instead of Y. Gold labels. And then let's print what the value of Y pred would be if we just calculate the value of the function without optimizing, right? So Y pred before optimization. This will be calculated if we just do this. Oops. And lastly, we also want to see what will be the final value after optimization. So Y pred after optimization. Hopefully this gives us the results. Okay, so as you can see, comparing the goal labels, even these first few values are vastly different from what is expected, right? There's quite a huge difference, but after optimization, we can see that the values are much, much closer as compared to the original ones. So yes, our model that we have defined just now is being optimized, and this is how you would go about defining a machine learning model using the basic NumPy library. Now, all this is well and good, but the problem is you cannot do all of these functions in the GPU to accelerate the numerical computations. Now, for modern deep neural networks that have millions of parameters, GPUs are known to provide 50 times or greater speedups. So if you go to this particular GitHub repository, which has done all these comparisons, I'll just show you the example of this one. So VGG16 is a quite a deep neural architecture. And here, this total milliseconds define how long it took to fine-tune this particular model on these various GPUs. And lastly, we have the CPU. So as you can see, even the oldest GPU that is here, the GTX 1080, it has 522 milliseconds as an execution time. On the other hand, the CPU takes, I think, 14 times or so much larger computation time to fine-tune this model. So as you can see, the difference is quite high. Now, to leverage this difference, like a computational power, the NumPy does not have any functionalities to do so. You cannot run NumPy models on a GPU. So you have to look at the PyTorch tensors, which enables you to do this function, use this GPUs. Now, to leverage GPUs from our tensor, we have to leverage the CUDA library. Essentially, this is the Compute Unified Device Architecture that was developed by NVIDIA. Now it enables programs to use a massive parallel processing power of GPUs. So this 50 times or greater speed up is not magic. It actually happens because GPUs are much more optimized towards parallel processing as opposed to the CPUs. Which is like so. Like GPUs are known to have thousands of smaller cores, so around 1024, 2048, or even larger, and they are optimized to handle multiple tasks simultaneously. On the other hand, CPUs are for SQL processing, so they have very few cores, like the Core i3, i7, or i9, and they optimize for handling one task at one time with higher efficiency. So GPUs are optimized for high throughput tasks that requires processing many tasks at once, even if each of these individual tasks takes slightly longer to finish execution. This is quite okay, but we just need to handle a huge number of processes at once. On the other hand, CPUs are optimized for low latency tasks, essentially that those tasks that require quick execution, like you want the results as soon as possible. And these include the system tasks and all of those things. And then GPUs have much more higher memory bandwidth as compared to CPUs. This essentially means that the amount of time taken to move some information from the RAM to the CPU is much more as compared to moving the information from a GPU RAM back to the cores. So faster transfer data between memory and processing cores. Now, let's say we want to do the previous process on a GPU. Now, although I did not plug into the GPU here. So, but yeah, let's see how to do it. So first off, we first need to import the torch library. And then let's define the data type we want to work with, uh, torch.float. Yep. This will ensure that all the operations in this torch architecture will be a floating type architecture. Sorry, a floating type data type. And then we want to specify the device that we want to run on, right? So it will be the torch dot device. Yeah. So yeah. So because my collab function, collab runtime does not have a G, yeah, yeah, I think it does not have a GPU. Yeah. So I'm specifying it as CPU, but in case you want to run it over the GPU, you can simply change the GPU, CPU value to CUDA. So this will ensure that all your processing will be done over the GPU instead of the CPU. But in my case, because I don't have a GPU in this lab runtime, I'll just run it on the CPU. Now, again, in the X value, instead of using the NumPy as we have done, we'll now use the torch itself. So now the lin space remains same. The starting range, the end range, number of values we want will remain same. And then we specify the device will be whatever we have chosen here. It can either be the CPU or the GPU. And lastly, we also need to define the data type should be floating point. And then we do and y equals torch dot sum. So let's see if this much is working as it. Okay, we don't need this numpy. If this is working as it should, yep, we have yeah. So first difference you can see that these are just the arrays that you got, but as soon as you use tensor, the variable type changes to the tensor here as well as here. So the whole thing remains same. We have 2000 equidistant values from negative pi to positive pi. Now comes the fine tuning. Now, okay, so the first thing, again, we have to define the random weights instead of using numpy like so. We'll change it to torch. How to do this? So it will be torch.random. We don't need the random Brandon. And then we'll define that we just want a singular value on the device that we specify and the data type that we specify. Okay. This should work. And we'll just keep on copying it to each of these coefficients. Again, let's see if this is working as it should. Yep, we have the random coefficients specified, and then the result before optimization is something that is vastly different from what the goal labels are. Okay, now comes the optimization part. So again, let's keep the learning rate the same for time step in the range of 2000. We keep the y-pred same. Now the squared function will be quite a lot different because we are using torch, no longer numpy. So it will be torch dot, no, just, yeah, no need for this either. Just do power. So y-pred minus y to the power of 2. And then since we return a tuple, we also want the summation and whatever is inside the container. So, yep. Now comes the gradient function. The gradient will remain same as it is. Summation is also done. Create minus a, and then finally, yeah. So this should run. Okay, so we have the values as you can see. From the initial 2920, we have got down to well, the results after optimization is also quite a lot similar to the original goal labels that we saw here. As opposed to 31, we have smaller values. So you can see the model, although it's not perfect, it is converging quite well for our task at hand. So as you can see, the syntax is quite similar to NumPy, but if you wish to train a model in Torch, this is how you change everything. Just ensure that all of your values are in Torch because NumPy and Torch are incompatible. Okay, now the problem is, as you can see, this was quite a small enough program where we had 4 different coefficients that we can manually write, calculate the gradients, and then optimize it. But for models that have millions of parameters, doing so manually would be quite a lot difficult, right? So the solution would be the leveraging the automatic differentiation function provided by PyTorch. So this enables you, as soon as you define a model and you wish to optimize it, the backward passes in neural net will be automated. So optimization will happen automatically. You don't need to write each of these, the millions of parameters manually and optimize them one after the other. Rather, it will happen automatically. And then as soon as you call the forward pass, the PyTorch on the backend will define something called the computational graph. So in this graph, the nodes will be the tensors, these values that you have, and the edges functions that produce the output tensors from the input tensors. Right? As once you have this graph, to calculate a gradient, you can simply do a back propagation through this graph, and you can easily compute the gradients. This essentially means that you no longer need to do the calculations here. You can simply just backtrack on the computational graph, and you will arrive at the gradient. So this also saves you quite a bit of time. Now let's go about training this. How do you enable automatic gradient differentiation, right? So we'll use the same function that we have here. Yep. And then this as well. Okay. Now, space will remain same, torch, and then let's, instead of calling device every single time, you can simply do torch dot set device and set default. Yep, set default and device. And let's just keep it as rather than hard coding, just pass in the device here. So this will ensure that any tensor that you create in this code base will be by default migrated over to the device that you specify here. So we can remove this argument, and then we can simply replace it with something like requires grad to true. This enables that the torch that you have defined here is expecting a gradient optimization, and this will force the PyTorch, like essentially hint to the PyTorch backend that we require a computational graph for this tensor as well. And then we'll just do this for every data that we have created, every torch that we have created. Oops, like the A's and C's and D's. Yep. Okay. Now it should run. Okay, so we have the results here, but again, although it's quite difficult to understand what is happening. And lastly, one thing we forgot to mention is that, again, we're just manually specifying everything here. So rather than doing it manually, we'll have to define it automatically. So since we have enabled request grad equals true, to this loss, we can simply call loss dot backward. So this will essentially backtrack the computational graph that you have developed in the forward function here, and then arrive at the gradient function, just this. And then lastly, we also have to optimize our A, B, and C. Yep. So that's where we have in here, as you can see, the optimization of A is happening as we have seen earlier, but we do not need to calculate the gradient like so. And then lastly, once this is done, we also have to ensure that the gradients are set to 0. Okay, so this A dot grad is the value that stores the gradients that we receive at the loss dot backwards. So in order to do okay, so let me just give you an example how this happens. So first we have to manually set them to none in order to ensure that the converging happens when we call the backward and there's no garbage value predefined there. So you have A, B, C, and D. Okay. Now for this, okay, so we will first see how A dot grad is actually stored. So let's see before anything. We'll see what each of these grad variables have in store for us. Okay. So there we have it. And then let's also see how this value changes at every 100th timestamp. So during training. And this, and finally, we'll have the results here as well. Now, one more thing, this loss function will return a tuple. So we want the value inside the container. And then, yep, should work. Let's see. Float object has no loss in this item. Backward. Let's see. Quantitative. Okay, okay. So here we should, it should be dot item. And then because this loss is a function with computational graph, we do not need the item. Okay. Is this start dot now grad trying to show a graph a second time? Oops. Yeah. We have to restart the execution. Correct. Where am I not passing because grad equals to equals grad equals to item equals one equals to code equals again. This format. Yeah, okay. So here we have it. Right, again, as you can see, the predicted before optimization closer. And lastly, we can, where is it now? after backward, it will be optimized. Gradient function of A value changes as it keeps on going down further below, as you can see here for each of these gradient variables. And yeah, so this is how you would go about defining a simple function that tries to replicate another function. And as you have just seen, we do not need to calculate the gradients manually. Rather, we just do a backward function here, and this gradients is calculated automatically. Now, now we have the basics on hand. We saw how everything is done, but let's now try to develop a simple neural network and in order to hammer in all the concepts that you have learned so far. Right. So first, let's begin importing the libraries. Torch. We will also need the GIAN from Torch and import import. No, let's just do import Torch .nn as and then yep. And then we'll also need an optimizer. So dot optim GIAN as optim. Okay. Now let's define our model, right? Let's call it linear regression. And we'll call the module from. We'll also need the initializer. Self. Do it. We'll also have a super function for this class, which is linear regression. And self initialize it. Okay, class is defined. We'll also, okay, so for, let's define a simple perceptron, right? So we'll define a single input and output. So let's call it 1. So equals to nn dot linear, which should take 1 input and then it will output 1. So essentially it is just 1 input and 1 output. Now, for this model, we also have to define the forward function, like we specify what this model does or how the input passes. So it will be self and the input value x. And then for this input value, we want to pass it through the previously defined linear layer here. So x. And lastly, we return the value x. Okay, so we have defined our small perceptron here. And then let's first now define the inputs. So we have to go with torch.tensor. And to it, we'll put in a list of values. Okay, so let's try to build a model that just multiplies every input with 2. Yeah. So 2.0 and 0.0. Lastly, for good measure, let's keep 4.0. Space it out. So it's for better readability. Yeah. So we have 4 inputs and the goal labels will be multiply each of these input values by 2. And 8. Okay. So we'll call our model here to initialize it. Linear regression. We also need to define the loss function. So let's call it criterion. Criterion, we do BD and not mean squared error. So we want, and lastly, we also want the optimizer to be the stochastic gradient Yeah, there we go. SGD. We want to optimize the parameters of our model that we have defined. And lastly, we also want to define the learning rate, which is called ILR equals, let's call it again, 0.01 for good measure. Okay, fine. And now comes the training. So how do you go about training this? So simple, again, we'll do the range of 2000. So for this time, we'll call epoch instead of time step. So this is the lingo that is used everywhere. Range of 2000. We want the output from our model, and the input will be X. Okay. And this will give us the output. So we want to calculate the loss, which will be given by the criterion, which is essentially the mean square error loss. To it, we pass the output and then the goal labels Y. And lastly, we also calculate the gradients by simply calling the backward function. And then we force the optimizer to take a step based upon the value of the loss. Again, we want to print what is happening. So let's say epoch starts with 0. So percentage 100. Oh, so 10. Well, equals 0. Let's not go to 2000. Let's keep it small. It'll take a huge time. Okay. So 1000. Yep. And then we just print what the values are. Oh. One out of 100. And then loss at each time step will be loss. Then just the value that we want. Fine. Okay. And then lastly, we'll also have to test our model to check if the model has trained well enough or not. So let's go with test equals dot tensor. And to this, we'll keep the value 5, let's say. Yeah. So ideally, it should give us 10. So let's check what the model gives us. Spread equals model X test. And then we print it. This is good enough. Let's see how our model does. Right? Let's call it net. Forward differentiation defined forward differentiation one. Okay, let's all this before. So that is defined now. Oh, there are indents everywhere. Oh, okay, my God. Let's keep these as it is. Yep. Or as well. And yeah, that should work. The parameter list net has one. Then automatic list file. Okay. There are no parameters here. There should be. Let's see what went wrong. SGD, what is this? One plus self time. What if I increase the number here? Linear 2, 1. Let's see what happens here. Something is wrong. Just two. But and we call default function. It answer called middle called let's see params. Okay. Mr. Spelling Sticks and why isn't this work? Yep. Correct. See, replace this with the original one. String and question we can't do this one. Change the method to there. How about now? See if it works out here. We have CUDA. We have no code launch. We have let's try this here. We have defined the function there. Now comes the training part. I don't need this again. Let's go again. Forward to save. Return X. We do not have the net there. Watch the near recursion. Stochastic gradient is in parameter. Spreader and the loss. The parameters. Where is this error coming from? Stop option. Let's try everything again. So we have the model. We also want the input. Starch. Dot tensor. 0.50 by 2.0. Let's keep it here. And y will be the labels initially multiplied by 2. Okay, so model cross linear regression. Define it's working. Then we solve the criterion to the mean squared error. And then the mean squared error loss. Measure the library often. There we go. Distance. It's not a thing. Let's see. Now test measure. Complex. So the range. It's in range. Let's keep it 100. We want the output from the models x is the input. We define x there. Go. Loss will be the value with x. Optimizer. And oops, first with the coin, the loss of backward. So that instead of the stochastic, let's keep it as hidden. Let's see where it goes. And we'll box snip. Let's use these. That see. Capital. It's not active already. Unactive. Keeps on coming empty. Why? Linear regression. Let's just define the parameter by itself, right? Let's call it image equals and then dot We don't need this. Just go. So it is not even identifying this dummy parameters. So it's called parameter to lists. What's going on here? Let's see if there is none here. Seems empty. But we did define the parameter list here, right? So spelling mistakes. Oh, okay. Okay. In and then that title, then this should be doing. Finally, this. Yep, now it's working. So as you can see, a small spelling mistake here can take up a lot of time. Anyway, forward missing a target. There is up here. I forgot to pass on the go labels. Okay, there we go. Optimizer step should also be a function call. And yeah, what else? And cracker, I'm going to look at function. Which one? Mouse. Garbage values, function defined. Loss should be criterion minus loss. Then loss of record is as it should be. Let's ensure again. We put the output instead of X. Yeah. Okay, so after the 100 epoch, we have 5 lines is actually just giving us 6. It should be 10. So quite a low training accuracy. So let's just increase it to this. And let's keep it. Let's see what happens if you just use a single layer perceptron. And then 1000 optimizer is SGD, linear is this. Sorry. Yeah, so as you can see, it is quite nearby 9.9, but let's see if we just increase it to the 2 parameters. Let's see what happens. What happened now? 5 character item. So with 2 elements, this cannot be converted to scalar. Hmm? 2 predictions. Oh, oh. Hmm. Then, yeah. Sorry, forgot to enable the second linear layer. Let's try that again. Quite similar. So yeah, so this is how you would go about creating a simple neural network with multiple layers, the optimizer that you want of choice, the criterion. There are many types of loss functions from analog loss across entropy, so on and so forth. You can go and exploring this in the official document page. And I'm happy to take them, but I believe I'm over time. Okay, that is all I had for today. Thank you for listening, everyone. Ratnesh sir, over to you.
Hi, Arpan. I have one question.
Yes, Shiva.
Yeah. Uh, First of all, I really appreciate the tutorial. It takes a lot of courage to do live coding because and no one does it. So you are a very rare person in that regard, and I really like that you didn't give up. And but my question is, when you do computational graphs through this auto grid,
Mhm.
is there a way to visualize it also? I can look it up on my own, but do
Yes,
yeah.
yes, yes. So a simplest way, like essentially what most people do, is just you plot, where did you go? Yeah, so you just save these loss values that you have and then just use a matplotlib to plot it somewhere. But if you want much more details as what is happening, I recommend that you just store the values that you get in what happened here. Yeah. So these values that you get here, these A grades that keeps on optimizing. If you want to jump deep dive into what is actually happening, I recommend you plot these values that you can see. Like loss function, as you can expect that while training the loss function, the graph will keep on decreasing. That's fine, but that doesn't give you much idea. But if you want to manually look at which weight is increasing, which weight is being decreased during the optimization, I recommend you look at these values instead.
Okay. Sorry, the sharing is disabled, but I believe
Oh,
you were also dictating, so I kind of got it.
yeah. Okay.
Thank you.